Morning, folks. Y'all doing okay? Listen, I'm sending around a sign-in sheet. This will be, I think it might be the last time. All of your classes should be doing sign-in sheets. This was the role that I pulled off this morning. If you're not on this list, and you should be on the list, like you're here and you think you're enrolled in the class, it probably means that you have an excess of fees. They have this new policy. It's sort of just as a gentle reminder to you to remember to pay your fees. Uh, that they'll drop you from the class. Don't worry, we'll get you re-enrolled if you're not on that list, but you'll need to go up front and take care of your fees. And if you have trouble with that, please come see me. There are lots of ways to take care of that, so that the university can help you with payment plans or whatever. All right. You have any news from the weekend? I have any big events? Any happy news from the weekend? It was sort of a ho-hum weekend for us too. It's okay to have ho-hum weekends every once in a while. All right. See, I realized last time, morning, gentlemen, that I forgot to do the concept test for this chapter 1. We'll have these with every chapter, and I'll borrow your book for just a second. Ryan, right? If you look in the back, all the questions that we'll do are in an appendix, pages that look like this, and so you can follow along. You'll need your clickers. Normally I'll spread this out throughout the chapter, but this week's is not very long, so. All right, these are all questions related to the chapter 1 material. And also, I'll have these type questions on the test, which, by the way, does anybody know when the test is? The first exam? It's when? Right, yeah, so that's not this coming Friday, but the next Friday. And that test will definitely cover chapters 1 and 2, and it'll probably cover the first part of chapter 3, just on vectors. All right, basic stuff about vectors. That's really just trigonometry again, so it's not a big sweat. Morning, James, right? Yeah. All right, so let's try this. Displacement x, which is in meters, is related to velocity v according to this relationship, x equals av. What must be the dimensions of the constant a in order for that to be dimensionally correct? Can y'all see this color scheme okay, Shane? You see it okay? It's in the back of your book too, all the questions. What must be the units of a? Just to remind you, you put in the units for x, put in the units for v, and then you want to make it dimensionally correct on both sides, the same on both sides. So you need to know what are the units for A in order to do so. All right, let's do about 10 more seconds. Stop at 1:30. Remember with these questions, if you don't get it right, you still get credit. So answer, you can guess or ask your neighbor. I'll go on to 1:30. Yeah, 1:32. Yeah, Ainsley. Okay. I don't have batteries. I'm sorry. Is it battery problem? I'm sorry, listen guys, if that ever happens to you, I recommend that you carry batteries. But if you ever miss a day, even if you just miss the questions, you know what, the class participation points, the clicker points, they're really meant there to be a guide for you. And as long as you come regularly, which Ainsley, I know that you do, and all of you come, because you're good students and y'all come regularly, as long as you come regularly, it's not a big deal if you miss a day or two or even 3 or 4. It's really if you miss like half the days of class, then you're going to fall behind on this. So sort of in between that third and fourth exam, practically everybody is going to max out their class participation. All right. So Ainsley, is just don't sweat it. All right. All right. So let's see a little bit across the board here. So I have x, which is in meters. V is in meters per second. So in order for this to be dimensionally correct, I have to have unit seconds here, and that cancels out and leave me with meters on both sides. So if it's seconds, then C is the right answer. All right. Um, a crate had these dimensions. If there are 3.28 feet per meter, then what is the volume of the crate in cubic feet? I know you're going to be inclined to pull out your calculator, and that's fine if you want to. But just try doing this by estimations, like round everything off to whole numbers, and see if you can get an answer. What's that? Oh, yeah. We're going to convert these units to cubic feet. Feel free to ask your neighbor if you like. More of you have it right than wrong, but you're sort of all over the board on this as a class. So ask your neighbor, ask a couple neighbors, see what y'all think. Hey, what did you put? I put B. All right. All right, I'm going to stop at 140. 140. All right, A is the right answer. Nice easy way to do that is I just say 1 times 1 times 1. So I have this crate that's 1 cubic meter. It's about this big, right? A cubic meter on each side. And then it's roughly, a cubic meter is roughly 3 feet. So then I can say 1 cubic meter that I want to convert to cubic feet. 1 meter is 3 feet. But what do I have to do to this conversion factor? I have to cube it, right, because the units are cubed. That gets rid of that, and that leaves me with cubic feet. That rough estimation gives me about 30 cubic feet. A is really the only thing that's close to that. Or if you do it out with your calculator, you get exactly 34. All right, a jet airplane climbs 15 at an angle of 15 degrees with respect to the horizontal and follows a straight line path for a distance of 400 meters. How much altitude does it gain? That means it travels this distance of 400 meters. And I want to know how high is it above the ground. Feel free to ask your neighbor. Class is doing pretty well as a whole on this so far, but a few of you have the wrong answer. Thank you, Claire. Everybody sign this, y'all? All right. Brandon Domingue, Desiree, Gary, Thomas. Okay, good. All right, about 10 more seconds. I'll stop at 150. 150. You're doing well. A is the right answer here. Uh, Remembering this is a triangle, right? This angle is 15 degrees. I want to know this. And so I say, gosh, what trig function do I use here? Right, I use the sine because I have an opposite and the hypotenuse. Sine of, the sine of 15 degrees is equal to y over 400. And then if I solve this for y, doing a cross multiplication, 400 sine of 15 gives me 100 meters. A is the right answer. Mass along with what two quantities make up the three basic quantities that we use? Mass, length and force, power and force, length and time, or force and time. Hey, Brandon. Hey, Sydney. All right, about 10 more seconds. I'll stop at 40. I'd expect some basic questions about the standards of mass length, but, you know, of math and those other two. Awesome. Let's see, D, force and time. We'll get to force. Force is not one of the basic quantities. Force is actually made up of these three quantities. So every chapter we'll look at particular things, uh, like force, energy, power, work, stuff like that. And we'll see that they're made up of these basic SI quantities, mass, length, and time. We'll see that they all build on one another. But those are our three basic quantities, mass, length, and time. This is a relationship problem. I have this expression y equals x squared. Which of these statements is best consistent with that expression? If y doubles and x quadruples, is that true for y equals x squared? Y is greater than x, is that true for y equals x squared always? If x doubles and y doubles, I don't know. It's Thomas, right? Thomas? All right, about 8 more seconds. I'll stop at 55. Oh. All right. So y'all are sort of all over the board. Listen, guys, you'll see questions like this quite a bit this semester. We'll see them as we go along. If you change one variable, how does it affect the other variables? And these are also really common for standardized tests. So I have a few of you that are pre-med. If you're pre-med or you're taking the GRE or whatever, it's just a really useful skill for you to have to be able to answer these types of questions, to understand if you change one variable, how it affects the other variable. And it's really just thinking about the relationship, the mathematical relationship between these two quantities. So I have y equals x squared. A lot of you put a. If y doubles, then x quadruples. So if I imagine that I have 2y here, what do I need to do to x in order to make this side equivalent to this side? What do I have to do to x? I have to increase it by a certain amount, but it's not 4. How much is it? Not what now? Not a half, but you're thinking on the right track. No, not 4. What squared will give me 2? Square root of 2. Right, so over here, I'm going to have square root 2x. See, I haven't changed the mathematical relationship. It's still the same. Similarly here, if I have y is greater than x, for y equals x squared, that's almost always the case that y will be greater than x. So for example, if x is 2, y is 4. But what if x is a half? What is y? Which is smaller, right? So that's not always true. It's sometimes true, but not always. If x doubles and y doubles, that's not true either. That would be a linear relationship, which we'll see quite a lot. That is, if I increase one by one amount, the other increases by the same amount. And so the answer then is D. If I double x, if I double this value x, then y increases by a factor of 4. So D is the right answer. But I understand why you put A. It seems like it should be A, but it's not A. The answer here is D. We'll see these a lot as we go through the semester, so just get used to them, and you'll get more accustomed to them, because like I said, you're going to see them a lot on the test, and you're going to see them a lot, okay, on various multiple choice tests. By the way, I know that you're starting to set aside time each day to study physics in your other classes, right? Did we have this talk yet? The talk about, half an hour to an hour every day? Did we have that talk? Yeah, so I know that you're already carving out that time. A good way to use that time is to print out the old exams. You even have some in the back of your workbook and start working through those problems. I suggest that you work through them without using the solutions and then go back and check your work. But pick one problem a day, two problems a day, and go through them. And by the time the exam comes in a couple weeks, you'll be good to go. You'll be going to bed at like 8 o'clock on Thursday night and all ready for the exam the next morning. Okay? That's true for all your classes. You should be doing that for all your classes. Half hour, that's not that long. Okay, which of the following is dimensionally consistent with inverse time? That is, which of these expressions will give me 1 over seconds? 1 over seconds. Please ask your neighbor what they put, okay? I know that's kind of awkward. All right, about 10 more seconds. I'll stop at 1:15. 1:15. Just guess if you're not sure. A is correct. Just put in the units for each one. So V is meters per second. And then I have X in the denominator. I like to write it like this. It just helps me to sort of keep things sorted. And so that's 1 over second. So that is time. Let's just look at these others right quick, okay? So I have V squared over X. V is meters per second. It's squared. That's going to be 1 over X. So that's B. C is X over T. Of course, that's just meters over seconds. And then D is V squared T. That's meters squared, second squared. That's my V squared here. And then T is seconds. So I just get meters squared over seconds. You'll have a couple of those. By the way, as you're working through those old exams, you'll notice that typically out of about 15 multiple choice and about 4 to 6 free response, it's probably going to have a few more multiple choice for y'all and maybe 1 or 2 fewer free response. It's just I've never had a class this big. Usually this class is 10 to 20 students, and now it's approaching 40. So that's what it'll be. But just be aware of that you'll have fewer free response and more multiple choice, and more calculations on the multiple choice. Okay? It'll be okay. Don't sweat it. It's going to be fine. Y'all are going to do great. All right? Okay. All right. Which of these is the definition for time? Feel free to ask your neighbor, look back in your notes, whatever you want to do. I'll stop at 35. 35. What is the current standard? What's the current standard? All right, A is the right answer. Your solar day used to be the standard, but it was changed, I guess, in 1967. It's changed some time ago. I think it was changed before that. But the current standard for time is based on the frequency of the cesium atom, particular isotope of cesium. And the standard meter is based on which of these? This is the current standard for the meter, past 30 years. All right, I'll stop in about 10 seconds. I'll stop at 30. Stopping at 30. Awesome, that's great. It's the distance that light travels. Remember, it used to be this bar in France, but that's not a very good standard for the reasons we talked about. So now it's this distance that light travels. And which of these is consistent with units for acceleration? Remember, acceleration is meters per second squared. Velocity is meters per second. X is meters. And t, of course, is seconds. All right, about 5 more seconds, or I'll stop at 120. 120. Just guess if you don't know. 2 more seconds. Let's see, we're all over the board. It looks like most people put D. Let's just check D first and see if that's right. I have V squared, that's meters per second, squared. And then I have 1 over meters. That does look like it's right. That gives me meters per second squared. Let's do these other 3 though. Meters per second, 1 over second squared. That's meters per second cubed, which of course is a measure of what? What is it? What? Jerk. Very good. Excellent. Brennan, right? Yeah, jerk. So I have V as meters per second. That's 1 over meter squared. That's going to be 1 over meter seconds. And then this V squared over T is meters squared per second squared, 1 over seconds. So it'll be meters squared per seconds cubed. Just playing around with units like that is really useful. And it's kind of fun too. Like you can just go home and you can create your own equation and you can say, what are the final units of this? It's a useful skill to have. And like I said, it can be lots of fun if you want to try it at home. Okay, so I say D here is the right answer. Let's do a couple more and then we'll take a little break from it. What is the point nearest the y-axis? Which of these points? Using the coordinate systems a lot in this class, so be familiar with them. Which of those points is nearest the y-axis? Nobody has these 2 answers, so I'll just get rid of them. All right, I'll stop at 50. And B is the right answer. The one nearest the y-axis is the one with the smallest x value, right? Negative 5, 2 is negative 5 over 2 up. Negative 2, 5 is just 2 units away from the y-axis. So D is the right answer. Also, don't forget your quadrants, right? 1, 2, 3, and 4. And then don't forget your angles, 0, 90, 180, 270, and 360. And then later we'll talk about that in terms of radians, but don't sweat that right now. But 0, pi over 2, pi, blah, 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 you know that. We'll see that later when we get into later in the semester, in next semester. Okay, a little bit of sig figs. Actually, let's stop there. We'll come back to this. Let's just take a little break. Normally, I'll sort of spread these out throughout the chapter, but not today. We'll come back to this. Let's return back to our definitions of displacement. Remember last time we finished off with that Seabiscuit clip? Y'all remember that? And we said that when we define displacement in physics, we define it as a difference in position. And so Seabiscuit, despite the fact that he's zooming around that 1 mile track, when he starts and finishes at the same place, then we say that his displacement is what? Is 0, right? So that's just sort of a quirk of the definition of displacement. But displacement is just a uh, a change in position. So let's say that I mark these places on the board. I'm going to call this my 0 point. I'm going to say these are meters, but I'm going to make them sure they're like half meters. I'll call this -1, -2. These are the positions, 1, 2, and 3. So it should be pretty apparent to you that if I start at 0 and I move to here, then my displacement, delta x, is going to be my final position minus my initial position. So if I started at 0 and I went to 2 meters, then my displacement is 2 meters, right? It's my final minus my initial. And similarly, if I start here and I go over here, what is my displacement? What is it? It's not just 2, it's what? It's -2. So with our displacement, we always carry that negative sign because displacement is what we call a vector quantity. I'll write that down in just a second. So if I start here and I go here, then my displacement, in this case, will be, I started at 0, so that's my initial. I finished at -2, so my displacement will be -2 meters. All right, what if I start here at 1 and I go here? What is my displacement? It's -2. So there my final is going to be -1. My initial is 1. So to find that position, I say 1 minus, or excuse me, -1 minus 1 is equal to -2. All right, let's try one other. What if I start here at -2 and I go all the way over to 3? What is that? That's going to be 5, right? So it's going to be 3 is my final position minus a -2, and so those go to positive. So that displacement is 5. Actually, a question or a stretch? That's a stretch. Okay. Let's do one more. Let's say I go from 2 to 2, -2. What's that displacement? Not just 4, but -4. Right, so that would be a -2, which is my final position, minus 2, which is -4. So whenever I'm talking about displacement, I have two things that are attached to it. I have the magnitude. Actually, let me write it on here. I have the magnitude, and then I also have the direction. I have the magnitude and the direction, because displacement is a vector quantity. And vector quantities have both magnitude, the value, whatever the number is, and they have a direction. Now in this case, our direction is very simple. If I have a negative value, that means in what direction? It means to the left, because in our right-handed coordinate system, left is always negative. And if I have a positive value, then that means it's to the right. And our magnitude is just the value that I have. All right, so for example, let's say that I have delta x equal -6 meters. Direction here would be to the left, and the magnitude would be 6 meters. Or if it were +6 meters, it would be to the right. Sometimes we give direction in other ways, and actually once we get past chapter 2, most of the vectors that we deal with will either be in 2 or 3 dimensions. And in those cases, we'll give the directions usually with angles. So we can give them in other ways. For example, we can use our cardinal directions, north, south, east, and west. We'll use those some when we're dealing with vectors. We'll see that again in chapter 3. And we can use up, down. When I say up, I would typically mean plus y. Down will mean minus y. I can say left, right. And what I mean by that is negative x direction, positive x direction. Uh, I can give it an angle, or I can give it vector notation, which we'll get into later. Well, I'll give you a little preview of it here. So let's say that my displacement is 2 meters to the left. The way I'd write this in vector notation is to say that my displacement, delta x, I'm going to put an arrow over it to denote that it's a vector, that my delta x is equal to negative 2, which is how I wrote it up here. That's a 2. Negative 2. But we don't know if it's up, down, left, right, or whatever. So we'll add this additional vector to it. We'll call this vector notation. We'll put a little I with a hat on it. Don't sweat this too much. We won't see it again until chapter 3, and then I'll introduce vector notation for vectors. And it's really simple. IJK, y'all ever heard of IJK in writing vectors? Yes, no? Yeah? Okay, some of you have, but it's really simple. You'll see when we get to that in chapter 3. All right, so we have lots of vector quantities in physics. Vector quantities have what? Magnitude and what else? Direction. So anything that has both a magnitude and direction, uh, I don't know, like displacement has both magnitude and direction. We'll also see that velocity has both a magnitude and direction and acceleration. Forces have a direction. And we'll see that many of the different quantities that we deal with will be vector quantities. And so chapter 3, when we get into vectors, will be very important. Right now, we're just dealing in one dimension. We're either up and down or left and right. So the only thing you need to be concerned with right now is plus and minus. Plus is to the right, plus is up, negative is to the left, negative is down. So it's pretty simple so far. We usually show the variables for vectors with an arrow like I did before, x with an arrow over it, or v with an arrow over it, a, f, force. Sometimes when we're dealing with those unit vectors, when a vector has a magnitude of 1, like with the I, we might see it like this, I, j, k. These are also vectors, and we'll see those in chapter 3. Right. Scalar quantities, on the other hand, only have a magnitude. What are some scalar quantities? See, this should be, okay, a speed is a scalar quantity. Speed is what's measured in your car. So like when you're driving your car and you look at the speedometer and it says, 35 miles an hour, or however it is fast as you drive, it doesn't give a direction. So it's the magnitude of the velocity. It's only the value. What are some other quantities? Ainsley, did you say something? Distance, right? So distance as opposed to displacement. When Seabiscuit travels around the track, he travels a distance of a mile, or however long the track is. So distance is also a scalar quantity. What are some others? Okay, mass. It doesn't have any direction attached to it. Any others? There are lots of others. What do y'all think? Length is that's a scalar quantity. A bunch of others, right? Time is a scalar quantity. It doesn't have a direction to it. Temperature, charge, all those things. Anything that's just a quantity that you measure, it doesn't have a direction attached to it like that. Um, let's try this little quick test. This one should be pretty simple. Which of these are scalar quantities? Get used to this sort of format. I like this, where I give you several options and one or more is the correct answer, and you have to pick which combination of those are correct. So which of these are scalar quantities? Mass, acceleration, speed, or velocity? stop at 35, 35. It's pretty good. C is 1 and 3, mass and speed. Whenever I work these problems, I always like to circle the correct answers, and then I go down and look for the right option. So it's C, 1 and 3. Okay, so like we've already said, speed is a scalar quantity. It's the magnitude of the velocity. The average speed, we're going to define in this way. We'll say that it's the total distance divided by the time. So if you leave your house, for example, and you travel 10 miles, at some points in that travel, you're going to be going 10 miles an hour. At other points, you'll be going 50 miles an hour. Okay, but when you come back, let's say that you took an hour to travel that 10 miles, then your average speed would be 10 miles divided by an hour. It would be 10 miles per hour. So it doesn't take into account all the different changes in speed that you had during your trip. It just takes what is your total distance traveled divided by the total time. So we'll write this average speed as just d over t. Usually when I use the letter d, I'm referring to distance here, and that's sort of how I'll discern it from displacement instead, where displacement or distance is the magnitude of the displacement. So if a runner traverses a 400-meter track in 60 seconds, if I want to find her average speed, then I just divide the two. I just say that v is the total distance divided by time. It's 400 over 60. Let's cancel. 6 goes into 40 about 7 times. So 7 meters per second. 7 meters per second. This is meters. This is seconds. So my units carry over. About 7 meters per second. So that's, a decent runner covers about 7 meters in 1 second. What's the displacement of this runner on a 400-meter track? Is 0, right? Because her initial and final positions are the same, but the distance that she covers is 400 meters. This probably just seems kind of trivial to you now, and it is sort of trivial, but it's important to get these definitions straight in your head. We'll also define average velocity, and you'll most likely have a question where I ask you to calculate the average velocity. The average velocity is a vector quantity, so it will have a direction attached to it, and it's based on the displacement. It's going to be our delta x divided by our delta t. Remember, we defined our delta x as x final minus x initial divided by my total time, which is going to be t final minus t initial. And of course, this will be in units of meters per second. So average velocity is a vector with both magnitude and direction. So if we were to look at the runner in the previous little example, what would her average velocity be? What's that? No, not 7 meters per second. That's her speed. What's her average velocity here? It's going to be 0 again because we have that x final minus x initial. So the average velocity in that previous problem is going to be 400. That's her final position minus 0. That's her initial. Or excuse me, no, I'm sorry. Her displacement rather is going to be 0 minus 0 because she starts and stops at 0 divided by what was her time? 60 seconds. So her average velocity will be 0 meters. This will make more sense when we get into graphs, which is next. Let's look at this graph. I have this position versus time graph. You will have a graph that you have to interpret on the next exam, on the first exam, I'll give you a graph and I'll ask you several things. Calculate average velocity, calculate instantaneous velocity or acceleration or distance, and we'll have several ways to do that. So let's go through this one. This one's pretty simple. I have this position versus time graph. Let's get used to reading these, okay? It might have been a while since you've read a graph like this, but this just says, as time progresses from 0 to 40 seconds, the position changes. So at 0 seconds, this person is at minus 20 meters, 20 meters to the left of the origin. At 10 seconds, that person has moved to the 0 meter mark, and on and on. Okay, so this shows over time what has happened to the position of this person. Then we can ask lots of questions. But first of all, we'll have a couple different things that we can find about graphs, and in this one in particular, we'll find the slope. And the slope of the line gives the average velocity over the interval from 0 to 30 seconds. If I find the slope of this line, I'll be able to find the average velocity. So I can find the slope going from here to here. Remember slope, how do we find slope of a graph? Rise over run. You're going to be doing this a lot in lab. You'll be doing it in this first chapter, or in this chapter, right, the second chapter. Um, not so much in later chapters, but in this chapter especially, you'll do a lot of graph interpretation. So we find our rise and our run. This is our rise here. This is our run. It's important to ask yourself, is this a positive or a negative slope? Does this graph have a positive or a negative slope? It has a positive slope. A graph with a positive slope will look like this. A graph with a negative slope will look like this. It's because of this value, the rise. For this one, the rise is positive. If it's like this, the rise will be negative. Let's see, the slope of this graph, it goes from minus 20 up to 40, so this rise is equal to plus 60, and the run is from 0 to 30, so it's equal to 30 plus 30. So my slope here is going to be what? It's going to be positive 2, which is also going to be my average velocity. So my slope is equal to plus 2. My average velocity is delta x over delta t. This is really just rewriting the rise over run. That's going to be 40 minus 0 meters. Oh, I'm sorry, 40 minus negative 20, yes. Over 30 minus 0, and that's going to be 2 meters per second. Or notice also that you can find it at other points. Because this line is a straight line, I can find the average velocity at different intervals. So for example, I could instead do 40 minus 0 meters. What would be my time interval for this? If instead of doing 40 minus negative 20, I'm doing 40 and 0, what would be my time interval? 30 minus 10. So here I'd have 30 minus 10. So that would also give me 2 meters per second. We'll see this with graphs. This is a nice linear graph. Likely the graph that you'll be dealing with on the exam will be a nonlinear graph, but I'll show you how to deal with that. It's fairly straightforward. Okay, I'm sorry. I was going to, because the line is straight, it's linear, and the velocity doesn't change. I did this before, but the velocity, the average velocity from 10 to 30 seconds is the same. That's what I did on the previous page, where we had 40 minus 0, 30 minus 10 is 2. All right, let's look at this graph. This is a nonlinear graph. So here you don't have a straight line, it has curves. This is more likely what you'll see on the exam. It describes the position versus the time. And I can find the average velocity for certain time intervals. So let's say I want to find the average velocity from 0 to 10. This is my 0 time. This is my 10 time. I'm looking for this slope. So that's going to be, what is the slope of that line? It's going to be positive 1. So from 0 to 10 seconds, my rise is 10. My run is also 10. So it's going to be 10 over 10, which is check, check. All right, so here you're just finding the right sig figs. If you do this in your calculator, you get 290.136. So what is the right answer with proper sig figs? Oh, y'all doing great on this. Just a few more seconds. I'll stop at 52. 52. Awesome. Uh, 91 is, or excuse me, A is the right answer. Because when you're multiplying numbers, you keep the lowest number of sig figs. Here I only have 2, so that's the right answer. Why does no one ever die of starvation in the desert? Because of all the sandwiches there. See, that's what you get when you do well on a question. A good joke. All right. Um, The speed of a boat is given in knots. In the SI system, what would that be? Meters, seconds, meters per second, or kilograms per second? All right, I'll stop at 32. 32. Awesome. C is the right answer. Meters per second. Distance over time. If x is acceleration, if A is acceleration, that's meters per second squared. V is velocity, that's meters per second. X is position, that's meters, and T is seconds. Which of these is not dimensionally correct? So which of these is incorrect? Let's do about 15 more seconds. So 120. Let's guess if you're not sure. 120. C is right. You need to get quick on these, okay? I know it seems like you don't have much time in class, but to answer these, but it's for a reason because on the test, you'll need to go through these, which are relatively easy, quickly, so that you'll have more time to spend on those questions that just require more time, just more thought, more calculation. So get really good at this. Practice it. There's questions on old tests. You can look in the homework. There's practice there. Go through and just put the units on each one. Seconds, X is meters, V is meters per second, so that's going to be seconds over meters. I flip it because it's in the denominator. All right, that one's correct. A is V squared over X, meters per second squared, equals meters per second, but it's V squared, so those are both squared, and then 1 over meters. Those cancel. That one checks out okay because they have the same units. V is equal to A over T, meters per second, meters per second squared, 1 over seconds. Oh, wait a minute. That doesn't work, right? Because that's not units for velocity. That's units for what? Jerk, yeah. All right, so C is the right answer. Let's just do this last one. I have seconds squared. Remember, I don't worry about the 2. It doesn't have any units. Meters, seconds squared over meters. So this one cancels, and that one checks out okay as well. All right, just a couple more. Which one of these choices represents the preferred practice for sig figs? Adding up these numbers. If you do this in your calculator, you get 57.573. All right, I'll stop at 35, 35. Okay, D is the right answer. When you're adding numbers, you keep the lowest number of what? Decimal places. So here the lowest number is no decimal places. So D is the right answer, which is what y'all put. So is that the last one? Okay. Uh, see, we have a minute. I don't like to let y'all out early. Sorry, but I will today. So you get out uber early today. But I'll see you on Wednesday, okay? We're going to carry on with chapter 2. We'll probably finish it by Friday. and then we'll pick up with chapter 3 on Monday, okay? Do that homework. You can do the chapter 1 homework, begin on chapter 2.